I've just spent the last month creating an emulator for a Z80 CPU from the 1970s, and then I used that emulated CPU to emulate a Sinclair ZX80 computer from the 1980s as well. And so I'm going to demonstrate that in this video, and then after that I'll go on to talk about how I created the software and go through some of the source code itself. So on the screen I'll just do a tree of what's in the current directory. So I've got subdirectories, not ZX81, so that's the computer I'm going to emulate next, hopefully. So I've just started porting that, but I haven't actually done anything with that yet. The ZX80 is the one that computer which I've emulated using the Z80 emulation, and the Z80 source code just contains the things it needs to drive the hardware, whereas the Z80 CPU is emulated here, and I'll go through, like I say, the source code a bit later. And then I've got the ROMs, got a ZX80 CPU ROM and the ZX81 ROM as well. And if I scroll up a bit more, I've got, then the only other thing I've got is a directory of display drivers. So I've created this in a way that I can add display drivers, because ultimately I want it to run on an ESP32 microcontroller where I've got an LCD display. So hopefully if I can get it to run the ZX80 and ZX81 to run on the ESP32, all I have to do is create a display driver, which is a keyboard driver as well, and place it there. But to actually start this, so it creates one emulator which emulates it in the terminal, which I use for debugging, which I'll demonstrate later. But this graphic one is the one that I use, which uses the X Windows system on Linux to actually display the graphics, and then just give it the ROM it requires, which is a ZX80 ROM. When I start that up, it opens up an X Windows window here, and you can see I've got the K prompt there. So this is now running my emulator using that ZX80 ROM, giving it to the Z80 CPU emulator, and I get the prompt, and I can actually type in a program here. So I'll just type in a quick example program. So for A equals, and I try and remember all the keys. Let's make it 0 to 255, and then 20 print character string. I'll do the print out all the characters. See if we can remember the $sign, which is U, and open brackets A, and then I'll put a semicolon and a space after that, another semicolon, so I'll display them across the screen, and 30 next A, and I can run that program, and there it is. It displays the character set for the ZX80. Now you see when I pressed run and then hit return, there's a little pause. Now normally on the ZX80 that would be a blank screen, because it can only run, or the ZX80 computer can only run or display a blank screen. But because I'm displaying it on an X Windows bitmap, the bitmap is always there permanently. So one of the advantages of this emulator is the screen doesn't blank out when it's actually running and doing something. And so at the bottom of the screen you see the error at 0:30, which means it came to the end of the program naturally, and it does everything that the ZX80 does. So I can move the cursor up and down in the listing window, and I can go into edit line. So that was one of the good things about the ZX80 and 81, is you could actually go back and edit lines. Some computers you couldn't do that on. So if I put some rubbish in there and hit return, so that's then edited that line, and then when I run it, it gives me an error 2 on line 20. So I can also hit list, which just gives me that listing, or hit Q for new, and that'll clear the program space. So list, and it's now gone. So that's just a quick demonstration of the actual emulator in use, and now I'll go through some of the source code and explain how it was put together. So if I list the files which are actually in this project directory, in the actual root directory I've just got some files for building and debugging. The only source code I've got here is common.c, where I keep some common code which just is shared across everything, some just functions which may be useful anywhere. I've got ZX81 directory and ZX80 directory where I put the actual source code for, it's basically the hardware, so it emulates the hardware of those machines, which, and when I show you the source code, you see there's not much there because they don't actually do much. They're real geniuses at Sinclair because they use so many techniques to cut down the cost and cut down the amount of stuff that you needed, that it's the actual code in the ROM which is the magic part. Then I've got a directory called display where I put all my display drivers. So I've got display drivers currently for X Windows, which you just saw, and also a display driver for terminal, so I can run it in a terminal window like this one, so it comes in handy when debugging, and I'll show you that in a second. I've got a directory for ROMs where I keep ZX81 ROM and ZX80 ROM, and then a directory Z80 where I keep the emulation for the Z80 CPU. So if I just change into that directory right now, and I'll open this source code up first. Just take a second to open. Okay, so I've got the source code here for just the Z80 CPU. Now, actually, this is very simple. So it's weird, this particular project, because it's simple and complex at the same time. The actual code itself is really simple, but because the Z80 CPU has over 500, I would say, opcodes, you have to emulate each of those opcodes, and so there's a lot of stuff to type in, and most of it's copying and pasting, because as you'll see as I scroll down, I'll show you that most of the stuff, it's all basically the same stuff but copied again and again and again. So just a few things to point out in the actual variables themselves is I've got this Z80 memory read only, so I can flag pages of 200 up to 256 bytes for anywhere in the 64K memory range as being read only. So when I read in a ROM file, I can flag that part of memory as read only. That way, if anyone's running a program, it can't accidentally overwrite the ROM file, which you wouldn't be able to do in a normal computer, and so you won't get unexpected things occurring if someone's written a poorly written program. I've got Z80 memory, and that contains 64K, the registers, and the I/O mapping space and everything. So it's all just the memory is just a big array of characters, 8-bit characters, and all the operations are just moving stuff from one piece of memory to another piece of memory. And then I've also got mirror memory. So on the ZX80 and ZX81, to actually draw on the screen, they mirror the RAM up into high memory. So the low memory RAM is 4000 hex, where it keeps all the system variables, the programs, and what's on the display. But they mirror that up to the address C000 hex, and that's where the hardware can detect when it needs to actually update the display from. So that's part of the magic they do. So I needed to put a way in to mirror in one piece of memory to another piece of memory, so that when you write to 4000 hex, it automatically gets written to C000 hex as well. It doesn't actually do that. All it does is when you read it, it knows to read back from the appropriate memory that's required. I'll scroll through a lot of this stuff. So some of the stuff down the bottom is just handling getting bytes and getting words. The reason I've got functions to do that is so that I can detect if someone's written to a wrong piece of memory or something, so I can flag an error. And it's all to do with the actual debugging of the system, because it's really difficult to debug a CPU. A normal CPU is difficult to debug if you're written in assembly or machine code, but when you've actually written one yourself and you know that there might be bugs in your code, which is the emulation, not just the program, then it becomes a big nightmare to decode. So I've got stuff for setting flags as well in the CPU. So this is so go past the memory. So this is the main part of the code. So it's a function called execute, and all this is a loop, and it just goes, it says get what's the program counter, that's an opcode which needs to be executed, and it executes that, and it goes around the loop again, and what's the next one, and what's the next one. And all you do is in this loop you just put all of the opcode emulations. So it starts so I've got some stuff here which is to do with the debug terminal, which I'll demonstrate when I bring up that in a little while. And just below that, so here is a switch statement, and it just switches on whatever the opcode is that you've read, and it says if it's opcode 0 then it's a NOP instruction, and so all that does is nothing, and it just goes increments the program counter. But all of these other things, so load BC with A, it's just a matter of copying register A into what's pointed to by BC, and then increment the program counter, and that's all these are. So there's about 500 of these. I haven't done them all yet. I've got to complete them, and it's all a matter of just moving memory from one place to another. Even if it's a jump instruction, what it's doing is it's moving memory from a piece of program area into the program counter, which is just memory. So just every single one of these instructions is moving memory from one place to another place, and then whatever flags need to be set, like here, it then sets appropriate flags. Not all instructions set all flags, and some instructions, like this one here, don't set any flags at all. So it's a matter of going through the data sheets, seeing what needs to be set, what needs to be moved from where to where. And I've got this stuff which doesn't compile into non-debug code, but when I compile it as debug, it gives me information about the mnemonic that's been executed. And that way, actually, I've got something for free, because when I run the program, all I have to do is output the mnemonic variable each time around this loop, and I get a disassembly of the actual code running. So that was very handy and very essential for debugging as well, because there's only about half a dozen errors I had. Some of them were typing errors, and there was a couple where I misunderstood what the instruction was supposed to do, and so I wrote the code wrong. And those ones took a couple of weeks to actually delve through the code. I actually ended up starting to decipher what the ROM was actually doing, what the Sinclair ROM was doing. So some of the ROM I know what it does. I've gone into the program area, syntax checking and things like that. But I finally got to the end of that, and so hopefully now when I go to do the ZX81, because it's such a similar computer, hopefully it won't be too much work to actually do that. So to get to this stage where I've got a ZX80 emulation going, took about a month. The ZX81 one, which hopefully shouldn't take so long, but I've got other features because I need to be able to load tapes and save to tapes and things. So there's a bunch of other stuff. So it might take a little while to get the next version out, which will be the ZX81 one. But that's all there is in the code. I'll open up another bit of code as well. So if I go into the ZX80 directory and look at, so you see this ASM file, that's the disassembly that I wrote, which helped me in debugging the system. But if I look at the actual ZX80.c file, there's very little to this. So I've put the character set in there. So the character set isn't on the ZX80 and the ZX81 isn't ASCII. So I had to define my own character, well, what the actual character set of the ZX80 is, so that I could decipher what was going on with actually doing stuff in it. And this is where I've deciphered some of the memory stuff and what functions do. So I put my best guess into what some of the calls are in there, and this is just for reference only. It doesn't actually doesn't actually go into the actual compiled version of it. And then there's things like the error. So also, when you see the actual manual itself for the ZX80 and ZX81, they give you the system variables and their memory locations and the error message codes as well. So there's lots of useful information in the manuals. Apart from that, I went to the data sheets for the Z80, and I had to get a few of them because there are small errors in some of the data sheets. So you have to cross-reference a couple of times when something doesn't quite look right. But the main part of the code for actually emulating the computer itself, what it does is an initialization. So in this case, it puts in the actual window title of the Sinclair ZX80, I've decided to put in there. So on the ZX81 one, because they look very similar when they're running, I'll just have something different in the title, ZX81 in the title. Just call an initialization for the Z80 CPU. It's like booting it, so it sets addresses back to 0, data set bus back to 0 and things. This is where I set up the mirror memory, so 4000 hex gets mirrored to C000. Now the good thing about emulating is I can give everything that's not ROM, I can make RAM. So effectively it's up to about 64K of RAM, but because this memory, which is 16K, is mirrored, you only really get 16K of usable memory, which I guess was the maximum you could plug on onto the actual system. I do remember on ZX81s there was a Memtech memory expansion, for sure. I'm sure they were 32K or something. I guess they must have been switching pages to memory or something. I don't know. I'm not quite sure how you got a 32K RAM pack on the ZX81. Now I load the ROM file, which is an argument passed into the actual program, so you can decide whatever ROM file you want to load at the time. I haven't implemented load and tape files, but the second argument would be to load tape file automatically. Then I register a bunch of callback routines. So the thing about the Z80 emulation is I can call back every clock cycle. So if there's something in hardware that needs to be done on a particular memory address, I can get a callback for every clock cycle and decide when something needs to occur, and you'll see later on in the code how that works. Also for I/O ports, because the Z80 has an I/O port range, so 0 to 255, and I can register for callbacks to specific ports, and I can decide what to do on those ports. And then I just say execute and then boot address, which starts the execution off of the actual Z80 ROM. And then this is after when I press the escape key and coming out of the actual application itself, so it frees up memory that it's allocated and closes windows and things if it needs to. So this is the first bit of the code. So keyboard callback. So when an I/O port for the keyboard gets read, it will call back this function, and I can decide depending on what was pressed. So it'd be a matrix, so I decide on how the address of into the matrix is, and I decipher that into actual character, which is done in this bit of code here, and it just returns a result back to the Z80 CPU. So Z80 CPU thinks that no one's pressed a key, or someone's pressed a key and it was this value. So that's just emulating the keyboard on the ZX80. And then the display, so there's a port which all it does is for every blanking period on the screen. So in the olden days on a CRT display, where an electron beam scans down the display, when it gets to the bottom of the display, it has to move the electron beam back up the top left corner of the display from the bottom right hand corner, and that takes a little bit of time. And during that time it does things like it synchronizes the frame, and it does the execution. What the ZX80 does, and ZX81 does execution of the actual program that you're trying to run, whereas when it's updating the display itself, that's all it does. It just updates the display, it spends all its time doing that. So that's all it does in here, is refresh the display when it comes to that blanking area. And then this is the clock callback, which calls back on every single address which changes, and then I can say, okay, on the address bus A0 to A15, if bit 6 or bit 15, if those are both not set, because I've got an inverting exclamation mark here, if they're both low, or the refresh register bit 6 is low, then it triggers an interrupt. So it does that here. So that's how it emulates the hardware. So it says if certain conditions on the pins of the CPU meet a certain criteria, then I can trigger an interrupt in this particular case, which is to do with updating each scan line of the display in the ZX80. And I say not every clock cycle, but every 100,000 clock cycles. What we do is display the keys. I can't. What does that do? I think that just does a key scan. Oh, that's right. It's not display the keys. It's in the display library. It reads the keyboard, and then on this line down here. So it's looking for the M1 pin going low and A15 going low, and that's to do with updating the display. So this is in this particular bit of the code. Unfortunately, my cursor's now stuck on highlight. But in this bit of the code here, it just updates the display. So it decides if memory word, so this is part of the system variables of the ZX80, and it decides if it's the first character on the display it's displaying, and then it moves the scan line to 0. And the reason I needed that was if I didn't have this, my display would roll like the vertical hold was out, like it wasn't latching onto the top of the display. So with this, it keeps it a solid display, and then it decides on the data bus if bit 6 is low, then it's an actual code which the ZX80 has put out there to actually be displayed on the actual display. So it gets the display which is a byte of data from the character map, and it goes through each of the bits, and it will plot them on the display if they're supposed to be plotted on the display here. And that's all the code there is for emulating a ZX80. There's very little. So the actual CPU emulation itself, there's tons of it, but it's all very similar. Every single opcode is basically doing the same operations, but just moving between different memory addresses. And the actual computer emulation, which is in here, is very basic. So there's an operation for reading the keyboard and an operation for writing to the display, and that's all. So finally, I'll just show the debug build of the actual system itself. So if I just go up a line so I can just rerun this program. So it starts off terminal ZX80. So the previous one was graphic ZX80, but the terminal one just runs in this terminal window and emulates it in here. And again, the arguments are the same as the graphic one, and just takes the ROM name. So when I run, it comes up with this debug terminal. All this is displaying memory locations, so it's not complex stuff, but I've done it. So if I turn off breakpoints and turn off halt on breakpoint on halt, and just type G for go, and there you are. You can see that it's actually emulating it in the terminal window, and I can type in all the commands I would normally, and you can see popping up down the bottom is just a line of code showing that it's running mnemonics on the actual Z80 emulator itself. And if I hit the / key, I can go into a break. I can break it into the code myself, and then I can look at the addresses of where it was. So you can look at the program counter. So at the minute it was updating the display because this is in the higher part of memory. If I type M4000, I can see what's in memory at address 4000. And this is the display area, so it's full of these 76s, which is a halt instruction, but that means a new line on the display. And the bit of memory above that, this is the system variables of the ZX80, and then below that is just clear memory. So as you type a program in, it shifts all of these, actually shifts the display, I think, up into higher memory, and the program goes in below the display memory. And if I type memory 0, so this is the top of the actual ZX80 ROM, and on the right hand side here, originally I had these as ASCII characters, but I noticed that because the character set is completely different for the ZX80 and ZX81, I put the ZX80 characters over here, and then you can start to see things over here like the keyword lookup table down here, where the last letter of each keyword is inverted, so it knows when, so it can pack a big lot of information in without having terminated characters. All it does is set bit 8 of the last character, so it knows where the end of each keyword is. And if I hit enter, it just goes down to the next page of memory, and you can just take a look for the ROM. And there's only 4K of ROM, so it doesn't take long actually to go through all of the memory. So in this top area here, where the data looks kind of unusual, this is the character map of the actual ZX80, and then we come to blank memory here. Now the reason it's FFs here is because the ZX80 hasn't initialized this memory. So when you turn the ZX80 on, it goes from, if I go address 8000, it goes from address 8000 downwards. So if I go previous, and so there it is, and it puts, and when it decides, where does it, originally it looks through the memory, writes to the memory, reads from it, and decides where top of the memory is. and then it puts a stack at the top of the memory. So here's the actual data on the actual stack at the top of the memory here. So you can use a very simple debugging program to actually go through as part of the Z80 emulator. And when I compile it for actual release, none of this code goes into the actual release stuff. So the actual release code is about 60k, I think, and the debug code is more like 100k.